we move on to the force part of our midterm review here. So we started this unit talking about gravity, basically, right? Fg equals mg. So Fg is the force of gravity. All right, and the units of that are newtons. M, lowercase m, represents mass. The units of that are kilograms. G is gravitational field strength. This is due to the Earth. It's really at Earth's surface, but I'm not going to write that all right now. The units for that are newtons per kilogram. It's the amount of force for every kilogram of mass. All right. F net stands for, oops, I skipped force of friction. I'll come back to force of friction in a second here. F net is the net force, net or total or sum of force. That's going to be in newtons. F is force of friction. I guess I should have put more room. That's also in newtons. Mu is the coefficient of friction. Fn, that has no units. It's dimensionless, the coefficient of friction. Fn is normal force. Yeah, I definitely need more room for forces section here. And that's in newtons. Now the normal force, I'll draw over here for you in a second. A is still acceleration, so I'm not going to write that here. So we started off talking about the force of gravity. So something sitting on a surface, right? We represent it. It's got force of, we represent it with a dot, right? And it's got force of gravity, Earth pulling it down. It's got the force of the surface pulling it up. So Fn is your normal force. That's a force perpendicular to the ground holding something up. Gravity pulls on the center of mass towards the center of the Earth. All right. The key here is if V equals 0 or V is constant, the forces must cancel each other out. Forces must cancel each other out. They have to be equal, meaning the up forces and the down forces must be balanced. So if the force of gravity were to be, let's say, 100 newtons, the normal force would have to be 100 newtons. The force of gravity you'd say is negative, the normal force you'd say is positive. Force of friction acts on this surface here at the bottom, right? So let's say there's a force pulling it this way, right? Well, if it's constant velocity, the force of friction would have to be the same, but the opposite direction, resisting the motion. There's a table to find these coefficients. I'll put a note down here. Found in a table on equation sheet. All right. If V equals 0, V is constant force. If V is not equal to 0, or V is changing, the total force must be equal to mass times acceleration. The mass of the object times its acceleration. That's called Newton's second law. All right, so we looked at if a force was unbalanced, what would happen, would it move? We kind of tied together the force and the motion. So let's go ahead and look at the force problems in here. So, very first one, an astronaut has a mass of 75 kilograms, so that's M, on Earth, travels to a planet in a distant solar system on an exploratory mission. On this planet, using a force scale, so this is mass, that's not weight, that's mass. Weight, I should add that note, equals the magnitude of the force of gravity. So on this new planet, right, this astronaut stands on a scale, right, and the scale says the weight is 400 newtons. Well, that's the force of the scale. It's really the normal force equals 400 newtons. Therefore, force of gravity acting on it must be negative 400 newtons. All right, so weight is 400 newtons. Determine the strength of the new planet's gravitational field. That's G. So, whatever the force of gravity that is acting on her, that must be equal to her mass times whatever the gravitational field strength is. So we know the force of gravity is 400 newtons, right? You don't need to put the negative sign on here. That's okay. The magnitude of the force of gravity is 400 newtons, pulling her down. That's what the scale's reading, pushing her back up. The mass is 75 kilograms times G. So divide both sides by 75. All right, I don't have a calculator right here. Let me quick pause this and grab one. So 400 newtons divided by 75 kilograms. It cancels out. You get G equals 5.3. And look, it's newtons per kilogram. All right, on your equation sheet, it'll say G equals 9.8 newtons per kilogram. So you just use the same units that you see on there. All right, next problem. A net force of 30 newtons acts on an object initially at rest for a total of 10 seconds. The object reaches top speed of 8 meters per second in this time. So net force, that's F net. 10 seconds is time. Top speed, initially at rest, that's V initial. That's V final. All right, determine the magnitude of the acceleration of the object. So that's a motion problem first. 1, 2, 3, 4, 5. V initial, V final, V average, acceleration, displacement, and time. V initial is at rest, 0. V final is 8.0 meters per second. The average of 0 and 8 is 4. Quick put that in. Acceleration we don't know. Displacement we don't know. Time is 10 seconds. All right, so acceleration is change in velocity over time. So we have another motion problem here, really. So plus 8.0 meters per second. That's our change from 0 to 8 in a time of 10 seconds. So the acceleration is 8 over 10, which is does not need to be used, calculated on a calculator, but 0.80 meters per second each second, or meters per second squared. Now it says determine the mass of the object. Well, all right, so F net equals ma. I know it was 30 newtons of force that propelled this unknown mass with an acceleration of 0.8 meters per second squared. The bigger the mass, the lower the acceleration. The smaller the mass, the higher the acceleration. It's the product of the mass and the acceleration is what the net force must be. So divide both sides by 0.80. Now, this one is hard to see what the unit should be, but as long as you're using all normal units, which we are, the masses are always going to be in terms of kilograms. All right, did I put that on the... Yep, mass in kilograms. Okay. All right, so 0.30 divided by 0.8 is about 38 kilograms. All right, Let's see what else we have for force in this packet. One more, it looks like. Ah, yes, friction. Okay, warehouse worker pulls a 200-kilogram wooden crate across a wooden floor in a warehouse. All right, I'm going to need my old equation sheet here in a second. Oh, before I forget, let me just remind you. There's G right there. That's where G is shown, 9.8 newtons per kilogram. All right, 200-kilogram wooden crate across a wooden floor of a warehouse with a force of 660 newtons. All right, so let's draw that on here. Force is that way. All right, 660 newtons. Probably going to make that negative. We'll see. The car accelerates in the direction of the warehouse worker, so it's going that way. Draw a force diagram for the wooden crate using the dot below. All right, so we always have Fn and Fg anytime there's a surface involved. Now, it gave us materials, wood on wood, and when you see specific materials listed, that probably means you need to go to your reference sheet, right? Wood on wood. Two different coefficients of friction. Force of friction equals mu Fn. We're probably going to need that. So there is going to be a force of friction here, but it's not as big as the applied force. It's not as big as the applied force because it's accelerating that way, right? This tells us that the acceleration is in the direction of the worker here, so it's that way. You look up the necessary coefficient of friction and record it below. So it's sliding, so it's wood on wood, and it's sliding, so that's got to be a kinetic coefficient of friction, 0.30. There's no units on that, right? It's right there. You just read the number and write it down. It's kinetic. Determine the magnitude of the force of friction. All right. So the equation for the force of friction is the coefficient times whatever the normal force is. Now, the normal force must be canceling out gravity. All right, the normal force must be canceling out gravity. So I can figure out what gravity is. I'll know what the normal force is. So Fg, Fn is going to be equal magnitude of Fg, which is going to be mg. Now, often we just use, right, 10 for G. It just makes, 9.8 and 10. For instance, let me, as an example, 200 times 9.8 is 1960. 200 times 10 is 2000. Well, guess what? 1960 to 2 sig figs is 2000. So it's the same answer to 2 sig figs, which is what we typically are using. So using 10 newtons is a fine thing to do. So the force, the normal force is 2,000 newtons. In our problems, the normal force is pretty much always going to be just equal to, in magnitude, to whatever the force of gravity is. All right? So the force of friction now, I can plug that in. All right, over here. This is probably the hardest question on this practice sheet. All right. 0.3 times 2,000. Hopefully I made the numbers right. Sometimes if I don't plan out the applied force right, you can run into problems. So the force of friction is 600 newtons. So this is 600 newtons. Now, at some point, I have to make one of these axes negative, right? So it says determine the magnitude of the acceleration of the wooden crate. So we're going to use Newton's second law. F net equals ma. F net equals ma. Divide by m, divide by m. A is F net over m. Right? I know the mass is 200 kilograms. Well, what's F net? All right. I've got 600 pulling this way. I've got 660 pulling this way. I want to make that one on the left negative. So that means F net is negative 60, right? Because this 600 cancels out most of this one, and you're left over with 60 newtons, right? The net force is sum of the force. F net equals 600 newtons minus 660 newtons, negative 60 newtons. So it says magnitude, so the negative sign here doesn't really matter. So the acceleration is 60 newtons divided by 200 kilograms of mass. 60 divided by 200 is 0.30 meters per second squared. It's an acceleration, put the right units on it. All right, that brings us to energy, which I'll start in a new video.